Good morning, peeps. How we doing? Good job. Glad to hear it. Oh. Okay, so let us commence. So first, apologies about the chaos surrounding the exam. Yeah, that was a mess. And I will start grading the rest of it later today if time works out. Otherwise, I'll do it over the weekend. So I should have it done certainly by Monday. I hope to have it done sooner than that. If you have questions about any of that and what the numbers mean, obviously get in touch. I posted some tips on the problem write-up on Canvas for exercise 12.2.3, where there's some kind of weird algebra going on with those fees. And so I tried to share some ideas that would help there. So if you're having trouble with that, I would definitely have a look there. There have also been several questions about the factorial problem. It's useful to remember that you know that n is greater than 2 because of assumptions that you have. And that can help in an important place in that problem. But if you're unclear or you have questions, definitely ask me on chat or Slack or email or whatever. And I can try to give you a hand with that. Just as a general pro tip, I think that it has worked very well for people to take, when they've got some work and they're stuck somewhere, either they're not sure if they're doing a step correctly or they're not sure what the next step would be, taking a picture and posting it on Slack or sending it to me as an email, that actually has worked quite well. I can get a very clear sense of where you are, and then I can give you some feedback. If you're just like completely stuck, like you don't even know where to start, then probably a Zoom meeting is the more effective approach, because then we can sort of work back and forth and try to figure out what you do understand, what you don't understand. But if you've got somewhere and you have kind of a concrete question, a photograph, I can usually try to turn something like that around pretty quickly if I see it promptly. So definitely recommend. And you're welcome to do that on the final when we get to the final next week, which will be handed out next week and do the following week. If you're working on the final and you're like, I just want somebody to tell me I'm not doing something stupid, or I got to this point and I don't know how to, like, what to do next, totally take a picture and send it to me, and I would be more than happy to have a quick look. That's not a big issue, so I would highly recommend. Are there questions about anything so far before we continue on some of the stuff in chapter 10? Going, gone. Okay, then we will continue with chapter 10. So I'm going to share my whiteboard as usual. And move you up out of the way because you're a nuisance. Let me grab the chat so I know what's going on there. Okay, so we had gotten to where, we had talked on Wednesday about the meaning of Hoare triples and using them as a way of specifying the correctness of programs. And there had been a question about, well, what the heck what are programs? Like, what do we know about programs, and what kinds of properties can programs have? What can we put there? And I was like, we'll get to that. Well, today we're going to get to that, or at least start to get to that, because that's a very legitimate question. And so the first component of a program that we're going to talk about is assignments, which we've already talked about in some ways. We've seen assignments and textual substitution a lot. And the basic idea is, you have a variable and then you have some expression on the right-hand side, and we're saying, evaluate this. And then put its value in this variable. So we have to have a name on the left and some expression on the right. We evaluate the expression and we stick its value in the variable on the left. If you've done programming in any language, there has been some kind of assignment that you've interacted with. It can vary a lot, but there's been some way in which values were given to names. And this is something like that, okay? And so the simplest kind of program that we can have has the form, or simplest kind of, program we can have is an assignment. So the simplest specification that we can have is something like this. This is kind of the simplest possible program. So we have a specification of this very simple program that if Q is true and we do this assignment, then R ought to be true after we're done, okay? And so that's kind of as simple as it gets, and that's going to be our starting point. We will make it more complex as we move forward, okay? Does that setup make sense before we talk about how we would prove the correctness of something like this? Okay. So 10.2, assignment introduction. Oops. Says that this specification, or let's see, we'll say that the assignment X gets E, make sure I'm following the right language in the book, that X gets E satisfies the specification Q followed by X get something R, that this assignment satisfies this specification if, and it turns out it's actually if and only if, Q implies R with the substitution X gets E. So we're saying this assignment makes this true if and only if the precondition Q implies the postcondition, excuse me, the postcondition with this substitution applied to the postcondition. Okay? Questions about this? We'll do an example in a hot sec, but are there questions about this setup?
I'm a little confused about what you wrote after Q.
After which Q?
Oh, sorry. The first part.
Up here?
Oh, after 10.2.
Here.
Right here.
Okay. So here, a specification has the form a precondition, a postcondition, and an undetermined assignment. So that's supposed to be a question mark. Maybe that's, oops.
Oh, I see. I was confusing the bracket for something else.
Sorry. And my curly braces are not great. And I apologize for not writing terribly good curly braces. And this is meant to be a question mark, and it doesn't really look very much like one. That's a little more question marky. So the idea is we're going to assign something to X, and that this program that assigns some value to X ought to make R true if Q is true at the beginning. Did that answer the right question? Did we get there?
Yeah, we got there.
Cool. Glad to hear it. Okay, so then let's actually, are there other questions? My apologies. Are there other questions? Okay, let's do an example. So I'll start with an example that's in the book, then we'll do a slightly more complicated example that's not in the book. But let's start with an example that's in the book that's pretty simple. So we have the specification. X is greater than 0, and we assign something to X. And after that, X should be greater than 1. Okay. And we want to show that X gets X plus 1 satisfies that specification. Okay, with me? So then to prove that, we will use 10.2. This is true if, so Q is the precondition, X greater than 0, implies R is the postcondition, X greater than 1. With the substitution, X gets X plus 1 applied. Okay. Are you with me so far? Now, can somebody tell me why I needed these parentheses here?
Because otherwise it would just be the one that was affected, or part of it that was affected by the substitution.
Bingo, well done, yes. So substitution binds more tightly than anything else. That was something we talked about way back at the beginning of the course, but we haven't really talked about it much since then because we haven't done a lot of explicit substitution. We've tended to just kind of go, oh, and some substitution happened as we've gotten better at things. But now we're going to be doing explicit substitution again. So I wanted to remind people, and thank you for that excellent answer, that this binds really tightly, more tightly than anything else. So without the parens, a substitution would only apply to 1. So we would replace all the x's in 1 with x plus 1. Well, there are no x's in 1, so nothing would happen. Putting the parentheses in means that we apply the substitution to the whole postcondition. And that's the intent here, okay? And notice that because the substitution binds more tightly than anything else, what this statement is saying is we're going to apply this substitution to R, but not to Q, right? We need parentheses around the Q implies R if we wanted this to apply all the way across, but we don't. We only want it to apply to the postcondition. So here, that's what this is going to give us. We will apply this substitution to the postcondition, but we will leave the precondition alone. Okay? Does that make sense? Questions about that? Okay? So this is equivalent to, I'll just take that swoosh. So we'll do textual substitution. And we'll get x greater than 0 because we haven't applied anything to anything there. And here we'll replace x plus 1, x with x plus 1. Are you with me? Questions? Then we will do a little algebra over on the right-hand side. And we're just going to subtract 1 from both sides. And that's now true by 3 point, I don't know what. Sorry. Oh, my copy of the rules got buried. So P implies P is 371. Got there eventually. Boom. Okay. So that would be a proof that this program satisfies that specification. Does that make sense? Are there questions about that? So the pattern here is not super complicated. People get very excited when we get into chapter 10 because they feel like it's all new and amazing and I don't understand any of it. But the patterns are generally fairly simple. They're like recipes that you follow. And if you follow the recipes, everything else is stuff we've done, okay? And the recipe here said, that's what 10.2 says, is if the program is just an assignment, do this. That's all we have to do. So take the precondition, implies, the postcondition with the substitution, and then grind it out. And usually this is some algebra and some chapter 3 stuff and maybe some chapter 9, 8, 9 stuff, depending on the problem. But you're basically just do the substitution and then work it through, okay? So it's not like some wildly different thing. There's just a recipe that says, if you want to prove a thing of this form, do this. And we know how to do stuff like this. Okay. Questions? Okay, then let's do a more complicated example because complicated examples are fun. Okay, now let's look at our specification. And this is not in the book. So the specification is going to say that x equals r times a to the b and b greater than 0 and odd b. That's the precondition, so there's a lot there. Followed by some assignments, some program that updates R and B, so it assigns potentially new values to R and B, is going to give us the postcondition x equals R times A to the B and B at least 0. So this is the precondition, that's what we're going to update, and this is the postcondition. Now this looks really weird and arbitrary. It turns out that this, x equals r times a to the b, turns out to be an important part of a very nice algorithm for computing exponents quickly. So the kind of, and we'll try, if the time works out, we'll hopefully see the whole proof of that algorithm when we, before the end of the semester. But the short version is the simple way to compute like 2 to the 10th is to multiply 2 times 2 times 2 times 2 10 times. And so that algorithm takes n steps to compute 2 to the n, or a to the n, whatever n is. There is an alternative algorithm, which is what all of this business is about, that does it in log of n steps. So instead of taking 1,000,000 steps, it might take 20 steps, which is a huge improvement. And instead of, if you had 2 to the billion, instead of taking 1,000,000,000 steps, it would take 30 steps. So you can compute exponents much, much faster using this other approach. And then the other approach is really kind of not obvious though. So there'd be a legitimate question of like, can we prove that it's actually correct and not just some weird fever dream that Nick had someday? And this would be actually a piece of that proof. And like I said, hopefully by the end of the semester, we'll be able to see the whole proof worked out. But this would be a step of that larger proof. So we're going to have this x equals r times a to the b, and b is greater than 0, and b is odd. All of that is the precondition. We're going to assign something to r and b. And the post condition is that x equals r times a to the b is still true, and b is now greater than or equal to 0. Okay? And the claim then is that RB gets A times R and B minus 1 satisfies this specification. Okay, that's what we're claiming, is that this will make this thing true. And that's what we need to prove. Okay, questions? And I just realized I forgot to mention something on the previous slide. I apologize for the disconnect. We will come right back to this. But I do want to back up one and point out that here we proved that x gets x plus 1 satisfies this. But there are many other assignments that would have satisfied this specification. Letting x be x plus a billion certainly would have worked. Letting x be 7, like not even having x on the right-hand side, just say x gets 7. Well, if x is 7, it clearly is greater than 1. And we could put in a whole bunch of substitutions here and get that this is true. So this is not the only thing that satisfies the specification. It is a thing that satisfies the specification, okay? Now, over here, it's also true that this is not the only thing that satisfies this specification. It is a thing that satisfies this specification. It turns out to be a useful and interesting thing that satisfies this specification, but that's not going to be very clear now. That'll be more clear when we've got the whole thing in front of us. Right now, it's just going to seem a little arbitrary, okay? Questions about the setup before we do the proof? Okay, good. Proof. Now, 10.2 said, this is true if and only if we have the precondition x equals r times a to the b, and b is greater than 0, and odd b. That all of that implies the postcondition x equals r times a to the b, come on, a little bigger, and b at least 0, with the substitution RB gets a times r, comma, b minus 1. Okay? Which then is equivalent to, by textual substitution, x equals r times a to the b, and b greater than 0, and odd b implies, so now we need to do textual substitution here. X doesn't change. R gets replaced by a times r. B gets replaced with b minus 1. And b gets replaced with b minus 1. And this pair of parentheses around a times r is really, oh, hang on just a sec. I biffled this up. I completely wrote this wrong. My bad. I got ahead of myself. So R is A times R times A, and A doesn't change, and then B is B minus 1. Yeah, so I completely had the exponent in the wrong place here. So actually, these parentheses are not all that important because it's just a chain of multiplication, so we don't really need those parentheses. They would have been if my exponent had been over here where it doesn't belong and where I incorrectly put it, but where they are now, yeah, it doesn't matter. Okay. Questions about that? I sort of made a mess of that. So are there questions? Are we cool? Cool. So then I'm going to, and this is pretty common, especially when the precondition's rather complicated. So I'm going to assume the left-hand side. And because the left-hand side's a conjunction, I can actually sort of assume all of these somewhat separately. So I'm going to assume that this is true, and B is 0, greater than 0 is true, and B is odd is true. And now I want to prove that the right-hand side is true. And because this is an and, I could actually do this as two separate things. So I now need to prove the right-hand side, i.e. X equals A times R times A to the B minus 1, and B minus 1 at least 0. I could like do the whole thing as one big expression, but then I'm ended up like repeating a lot of stuff as I work through it. And so it's actually easier to treat these as two separate pieces. And often when you're doing these program specifications, it's not uncommon to have a situation where you have a big conjunct implies another big conjunct. And if you have that, it can be simpler to assume the pieces of the left-hand side conjunct, assume this, and assume this, and then prove each of these one at a time. And that's fine. And it involves less writing. You could always have assumed all of this and proved all of this. And you could always take whatever you get by like breaking it up and use that to assemble a proof that has all of it all the time. Just you end up with a lot of stuff written down. So this is easier to like manage the writing of it. So I'm going to do it this way, and I'll prove this part, and then I'll prove this part as two separate little pieces. Does that make sense? Questions about that? Somebody want to be like, you can't do that. I don't believe it. Okay, coolio. So let's do the first one. We have X equals A times R times A B minus 1. And by the symmetry and associativity of multiplication, I can move the A over so that it's with the exponentiation. And I get X equals R times A to the B minus 1. Now this, by rule of exponentiation, I can just join these together. And I have X equals R times A to the B. So this is A to the 1. This is A to the B minus 1. I add them together. I get 1 plus B minus 1, and I just get A to the B. Does that make sense? I'm sort of skipping some arithmetic steps there. So holler if you're like, I don't get it. And then this is true by this part of the assumption. So it matches that part of the assumption perfectly. Right? So this, let's, give me a different color. This here matches this, or actually I probably would have made more sense to erase, circle that. So that was one of the things we were assuming. So we're done with the first part. Does that make sense? Questions about that? Okay. Then let's move on to the second part. So we need to prove that b minus 1 is at least 0. And this is equivalent to, by some algebra that we've talked about before, that b minus 1 is greater than, oh, actually, let me do, let me move the 1 to the other side first. That'll be easier. So b at least 1. So that just, we added 1 to both sides. And now by algebra, this is b greater than 0. If b is an integer, being greater than or equal to 1 is the same as being greater than 0. And this matches that part of the assumption, and so we're done. True by assumption again. And so if we change color, this matched this, which came from here. And we're done. We have proved the whole thing. QED. Wah, 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 wah. So we started off with this specification, precondition. We're going to assign some stuff, postcondition. The claim was that this particular program satisfied that specification. That was true if the precondition implied the postcondition with the substitution applied. So all of this so far is purely mechanical. All we've done is taken the precondition, copied it, the postcondition, copied it, the program, copied it. So this is entirely mechanical, like no complicated brain cells involved. Then we did textual substitution, also pretty mechanical. Then we said, let's assume the left-hand side pieces and prove the right-hand side pieces. Again, pretty straightforward. Then we proved the two parts. And the two parts involve a lot of algebra. They're not hard in the context of the things in the book. They're not using like fancy properties of chapter 9 or something. But they do require that we remember and have mastery of our algebra skills from, whatever horrible moment in our life that we were subjected to algebra. So we need to be using our algebra well here. And that is actually often where people get stuck, is not on the book stuff, the stuff we're learning in the book, but more on algebra skills just being rusty. And so here, if you had something like this and you're like, I don't know what to do with this, right? That's a great question. Take a picture of this and send it to me and say, I don't know where to go from here. And I could be like, oh, join up the A's and use the exponent rule. And then you'd be like, oh, right, I can do that. and then you'd be here, and then you'd be done. So don't let yourself spend too long being stuck on algebra. This is not supposed to be an algebra class. If you're kind of stuck on a piece of algebra, that would definitely be a ask early and ask often kind of question, whether it's on a homework assignment or on the exam, okay? Questions?
Yeah.
Go ahead.
Do you not have to do anything with the odd?
Great question, full marks. Odd was a complete red herring here. And oh, I seem to have, in mysterious ways, put a period in the word odd. I don't know what that was about. Oh, and now I erased the O. That was, come on, erase the little period for me. There we go. Let's see, come back here. Odd. Yeah, so in this instance, odd didn't matter. Oh, and I seem to have erased, somehow I undid a green circle over here. It turns out we just didn't need odd here. And that's okay. There's nothing wrong with it, right? 10.2 says if all the stuff on the left implies the thing on the right, you win. And if it turns out you didn't need all the stuff on the left, there was more there than was strictly necessary, it's still totally true. It's just there was a piece you didn't need.
Okay.
And occasionally that happens. It turns out in this particular problem, you know that B, you'll know when you get to this point in this sort of larger problem that we haven't talked about, you end up knowing that B is odd, and it turns out it doesn't matter. And there's another case in that problem where you know that B is even, and there it does matter that B is even. But in this instance, it doesn't actually matter that B is odd. So it turned out we never ended up using it, right? And in some ways, this is odd. This is unusual because we're used to needing all the stuff in a proof. But that, in some ways, is slightly artificial. In real life, you know all kinds of things that you don't necessarily need to know. Like, it's also true that it's Friday, but we didn't need that it was true that it's Friday, right? That wasn't important for the proof. You know, it's also true that this class is happening on Zoom instead of in the classroom, but we didn't need that for the proof. So we could have added it to the list of things that we know, but it didn't matter. And it turns out here we knew that B was odd, but it didn't turn out to matter.
Mm-hmm.
Does that make sense?
Yeah, that makes sense.
Cool. Yeah, and so in the chat, it's been pointed out that, you know, we assumed the left-hand side was true. So this is all true, even if it's got some extra pieces. And if we still get to true, if we get to that the right-hand side is true, it doesn't really matter if there was some extra stuff on the left. Not really relevant. So, but it is surprising and weird. So it's super good that you asked about it. In general, if you didn't use an assumption, you should at least think about, like, did I need it? That, you know, because it's a bit like you've assembled the kit and you've got an extra screw. And then it's like, okay, is that because they just gave me an extra screw, or did I mess something up? And you should think about it, right? You should be like, I don't know, you know, go back through and check and be like, yes, I'm pretty sure I did everything right. And then you're happy. And in this case, we did everything right and we're good. But we might have, in going through it again, realized, oh, this only works because B is odd, and probably I should mention that. But there's actually nothing in either of these that only work because B is odd. So we're good. Does that make sense? Other questions? Okay. So there's a more complicated example of doing the correctness of assignment statements. Let me say a little bit, and there's some other examples in the book that I won't repeat in the interest of time, but obviously you should feel free to ask questions about anything I've done, but also anything that's in the book. Okay. Now, this was a single assignment. So far, all we've talked about is how to do one assignment. And a program with one assignment in it is kind of boring. So it'd be cool if we could talk about programs with multiple assignments. And so that's actually what we're going to do next. Questions before we move on? Cool. So how do we deal with multiple assignments, or what the book calls sequences?
I was curious how we how do you figure out what meets the specification?
How do you find this program? Yeah. That's a great question. So we will actually, after talking about sequences of assignments, section 10.3 is specifically about that question. Can we actually, given a specification, can we find the assignment that would satisfy that specification? Can we calculate it instead of having to guess it or have it given to us by some oracle? Like at the moment, this is just coming to you from me. It's like, Nick said this should work. Well, why, right? Other than Nick said and it turned out it worked. So in section 10.3, we will specifically look at how to try to find those programs. Does that make sense?
Yeah.
Cool. So we'll do that in a little bit, but we want to do sequences first. So sequences of assignments. So we often have situations where we have more than one assignment in a row. So we have, for example, Q followed by the assignment X gets E, followed by the assignment Y gets F, and that takes us to R. So it turns out that this is the program X gets E followed by Y gets F satisfies Q, X and Y get something. Oops. Undo. I want that to look like a question mark and not a curly brace. Oh, poop. Boom. And then the post condition R, if and only if Q implies, so this part looks the same, R, and then with both of these assignments applied as substitution in reverse order. And this is the part that always messes people up. So you do the last assignment as the first substitution. Okay. And in some ways, if you think about this in terms of time, we're first going to assign E to X, and then we're going to assign F to Y. So it's after the Y assignment that R becomes true. It might not have been true after the X assignment. We might not have gotten all the work done yet. And so this is closest to R in time, if you want to think about it that way. So it sort of makes sense that the first substitution we apply to R is the Y substitution, the last assignment. And then we apply the X substitution after that. Okay. And so that's the rule that we'll use to deal with multiple assignments. Okay? Questions?
This rule just applies to sequences, or I mean
Yes, it applies to sequences of assignments. We haven't yet gotten to things like if statements and stuff like that. But if you have a program that is a sequence of assignments, we will do the second or the last assignment as the first substitution. And if there were like 7 assignments here, the last would be the first substitution. The next to the last would be the next substitution, ... down to the first assignment would become the last substitution. Does that make sense?
Yep.
So as a example, our specification is going to be, make sure I get this right, that if x is, oh, and I was going to use color for this. So I'm using the rigid variable thing. So I'm giving a name to the original value of x. X is big X, and Y is big Y. Oops, that's supposed to be brown. Big Y. Put a little dude down there. So if that's our precondition, and we assign something to X and Y, that our post condition should be that the values of X and Y have swapped. And I'm actually going to go back in and fill in those 2 variables. But I'm trying to minimize the color changes because that takes time and it's probably tedious to watch. So now X is going to be Y and Y is going to be X. So if initially X had been 7 and Y had been 10, when we're done, X should be 10 and Y should be 7. So we've swapped the value of those 2 variables. Does that make sense as a sort of what that means? Okay. And then my claim is that the following program satisfies that. So T gets X, followed by X gets Y, followed by Y gets T. So that program satisfies this spec. So that's the claim, okay? And now to prove that, we would need to say that assumption, so X gets, and I'm gonna come back in and fill in the things once. So that all implies the post condition, X gets a blank and Y gets a blank, with this set of substitutions applied backwards. So the last thing we'll apply is Y gets T, and then we'll apply X gets Y, and then we'll apply T gets X. So we're applying these assignments in reverse order. And so this is a rigid X, this is a rigid Y, this is a rigid Y, and this is a rigid X. Questions about where we are at the moment? So I'm going to assume the left-hand side. And prove the right-hand side. And this is just all going to be a bunch of substitution. So we're going to have that x equals blank, y equals blank, all of this stuff, y gets t, x gets y, and t gets x. Oh, and then I got to fill in my blanks. So this is y, rigid y, and rigid x. And now that we'll just start doing the substitution. And I'm going to do the substitution one step at a time because I'm not smart enough to do them all at once and get it right. So I'm just going to do the first substitution. So x doesn't change. Rigid y doesn't change. Y gets t. And rigid x doesn't change. And so we got to fill in our rigid variables. So y here still, and x here. Okay? Are with me so far? Questions? Then, because I don't want to have to make a new screen, we'll come up here, and this is equivalent to, and we're going to do textual substitution again, because we're just grinding through the 3 substitutions. And now we have, well, x does get replaced by y, so this x becomes y. So y equals blank to be filled in. T doesn't change, and the other rigid variable doesn't change. And that would leave us with just one substitution. Fill in our rigid variables. So we have a y here and an x here. And notice that we have clearly accomplished something useful because we now have that y equals rigid y, and that was one of the things that we assumed. So we know that this part's true now, assuming that this doesn't mess it up. So we've gotten like half the problem done in some sense. And so we'll go ahead and do textual substitution one more time. And we get y gets rigid y, and t gets replaced by x. X gets rigid x. So put in the rigid variables. Y and x. And then that is true by the assumption. QD. Okay. So there was nothing hard about this. It was just a matter of grinding through the substitutions until we got to things that matched the assumptions. And then we were done. Okay. Now, this doesn't address Justin's question about, well, how did we come up with this program in the first place? Like, that's still a dangling question. But given that somebody gave us the program, proving that that program satisfied the specification was generally a mechanical exercise. We just needed to do the substitutions in the right order. If we had done them in the wrong order, it would not have worked. So we needed to do them in the right order. And once we did, then it all just played out. Okay. So that tells us this little program assign some new variable t, the value of x, then assign the value of y to x, and then assign t to y, allows us to swap the values of x and y, and it leaves us with this sort of temporary variable t, which we don't really know anything about after all this is over. Like, it was only there to facilitate the swapping, but it did allow us to make the swap that we wanted. Okay. So there's a question in the chat about, is the chapter going to stay this easy, or is there a smackdown around the corner? I think there's probably a smackdown around the corner. But it kind of depends. Like, I suspect that there are people who are not finding this easy. If all this is really straightforward and you're like, yeah, I totally get this, then maybe most of the rest of it will be fairly straightforward. My experience is that there are a lot of people that find this chapter hard. And so if so far we're doing okay, that's awesome. That makes me very happy. But when we get to, I mean, if statements are still pretty mechanical. Loops are the slightly weirder part, but they're also still mechanical. If you get past all the noise, the mechanics of what you have to do isn't that complicated. Well, I mean, okay, it's complicated in that there's often a lot of writing to do, but it's not necessarily hard, right? It's that there's a lot of writing here, but none of it was difficult, right? This just was a matter of like applying substitution 3 times. And so if you don't let yourself be overwhelmed by the size of things, the steps tend to be pretty mechanical or weird algebra. I mean, those are sort of the 2 things that happen. So I don't know if that helps any, but there we are. Okay. Questions about any of this? We've got 7 minutes. So let me say something quick about the calculating parts of assignments, which gets to the question earlier. We won't finish this today, but we can set it up and finish it on Monday. Oops. So if we have something Q, X get some expression E, R, and we don't know what E is, we want to figure out what E needs to be to make this true. Well, if we think about what does it mean for this to be true, if and only if Q implies R with the substitution applied, well, what that tells us is there are circumstances where we can figure out what E is by starting with this, which tells us what we need to be true, and trying to solve for E. Can we find an expression E that makes this work? So to return to our earlier example, let's imagine, or something like the earlier example, let's imagine we have the specification, Q, X gets something, and then when we're done, X is greater than 1. so the question is, can we calculate an expression E such that X gets E satisfies this expression? Or this specification, sorry. Wah, wah, wah. Oops, oh, too many. This spec. So what would that look like? Well, let's start with assume Q. We don't even know what Q is. And that's okay for the moment. Sometimes you need it, but sometimes you don't. I mean, you can kind of figure out what you need just from the post condition. Then R with X replaced by E is, by the definition of R was X greater than 1. X gets E, which, if we do the substitution, textual substitution, is E greater than 1. So this is telling us that the right-hand side is equivalent to E being greater than 1. So this follows from anything that makes E greater than 1. So we could use any value of E that is greater than 1. We could put that here and we are good to go, right? So this would, for example, follow from E equals 7 or 10 or a million. I mean, I just picked a number, but this would allow us to find an expression E that makes this true. We didn't specify very much here. All we said is that X needed to be bigger than 1. In a situation where there's more being specified, we might not be able to just like pick a number and make it work. We might have to actually calculate something more specific. But this is the basic idea, that we can use the substitution into the post condition, maybe using something about the precondition, and see if we can calculate a value for E that actually works. And if we do that, that kind of tells us what the program is, right? So this says that we could use the program X get 7 to satisfy this specification. So we were able to find the program from the specification in a somewhat mechanical way. And we'll look at a more interesting example of that on Monday, but that's sort of the basic piece. So if you're looking ahead, so the calculating parts of assignments, 10.3 is important. And then the next big thing is going to be 10.4, which is conditional statements, ifs. And that actually finishes chapter 10. We'll then jump back to, as time allows, chapter 12, because it turns out that loops were actually done in chapter 12 because we needed induction to be able to prove the correctness of loops. So we'll skip some stuff in chapter 12 and do the correctness of loops, which is section 12.6. So we'll skip sections 12.3. Yeah, we'll skip 12.3, 4, and 5, and then we'll do 12.6. And that'll finish proving programs are correct, and that'll finish the course, and we will all celebrate. And if you were all physically here, we'd have donuts or something, but you're not, so too bad. A reminder to do course evals. You should have gotten an email with links to all your evals for all your courses. Those are important. Time's run out, so I'll talk more about that on Monday, but make sure you do those. So are there any questions in the -1 minute that remain? Sorry to run long. I will see everybody later. Thank you all. Talk to you later. Bye. Oh, Emma, since you're still here,